Hello everyone, welcome to today's webinar, Simulation Showcase Series, Thermal Comfort and Implementation presented by IBPSA-USA's EPSI Committee. My name is Apurva and I'll be your moderator for today. While we wait for everyone to settle in, here's a quick rundown of what to expect. Today's session will be recorded and available through IBPSA-USA's YouTube channel. If you have any issues hearing the presentation, please try calling in by your phone instead of using computer audio. Since this is a Zoom webinar, you can participate by posting questions and comments in the Q&A tab at the bottom of your screen. Questions will be viewable by all the attendees, and there's an option to submit anonymously if you prefer. All right, first things first, for those who do not know us, we are EPSI, Emerging Professionals and Students of IBPSA USA. EPSI is a peer group under IBPSA USA focused on professionals less than 5 years of experience in building performance industry. We connect early career analysts with resources, networking opportunities, and leadership insights to help you grow in your career. And we are always looking for more energy enthusiasts to join us, so please scan the QR code and join our community. Now I'm excited to introduce our webinar series, Simulation Showcase. This series highlights innovative student projects using building simulation to tackle challenges like energy efficiency, decarbonization, indoor environmental quality, thermal comfort, etc. So we invited students and early career professionals to submit their simulation-based projects. Then the selected participants will now present in a 10 to 15 minute spotlight webinar, followed by audience Q&A, and our reviewers will assign scores based on our review criteria. And then the 3 finalists will be recognized at SimBuild in 2026 in Minneapolis. So today's session is one of the first in this monthly series running through February, where our presenters will share how simulation helped them develop real-world design solutions. So our topic for today is thermal comfort and implementation. And without further ado, I'd like to introduce our first presenter. Our first presenter is Mohamadi. He is a PhD candidate at Poznan University of Technology in Poland, specializing in energy-efficient building design, natural ventilation, and simulation-based optimization. His research focuses on thermal comfort and natural ventilation in residential buildings under climate change, using advanced simulation tools such as Autodesk CFD, OpenFOAM, and Design Builder. He is published in several journals and conferences and has received international research scholarships. His work bridges architecture, building science, and computational simulation to advance sustainable and resilient housing design. Let me stop sharing, and it's all yours, Mohammed.
Thank you. I'll start sharing my screen. Okay. Yeah, thank you so much for the introduction. And yeah, welcome to IBPSA Simulation Showcase. And I'm really happy to open this session for thermal comfort. Today, I will be presenting part of my PhD studies over optimizing natural ventilation strategies in multifamily housing in Poland. First, I will start about my journey a little bit, and then I will talk about my incentives, motivations, and introduction, then about my research steps, and finally about results and validation and discussion and outcomes, of course. I'm Mohammad. I started my studying architecture in Iran in 2014 until 2017, and then I joined Poznan University of Technology in 2021. By winning 2 scholarships, I was happy to join as visiting researcher at Austrian Institute of Technology and EMPA at Switzerland. And the first one was related to my PhD studies with AI-driven environmental simulations, and the second one was about developing digital twin in Dobendorf campus. My motivation about this thesis, or my thesis, is always about the climate change and global warming and these unfortunate graphs and diagrams that we can find with very simple search on Google. And when I started my PhD, already it was happening in Poland, and we were achieving unfortunate records every year. And with a research on the climate data on the climate stations in four main cities of Poland, Gdańsk, Poznan, and Warsaw, I find that these data information for the hottest day, for the developing the worst case scenario for running my simulation and studies for the date and the time and temperature and humidity. To have a general perspective of my research, of course, my research goes under the passive building design, heat rejection, and then natural ventilation with three different types of stack ventilation, cross ventilation, and single-sided ventilation. The innovations of my research are twofold, and as I talked about climate data already, integrated with CFD simulation and solar simulation to have or develop a very comprehensive thermal comfort index. And the second motivation of my research was to push the CFD simulations through a more complex and more real scale design architectural simulations. My research method and steps are in three steps. The first one was to study a general cooling or passive strategies that are applicable to Polish multifamily homes, and then modeling the geometry and running the CFD simulations and different kind of simulations themselves. And the final step was about to validating the results, discussion, and outcomes. I started with analyzing the famous multifamily buildings in Poland in a graphical way. I did over 300 flats, and unfortunately it gave me almost nothing or not any specific data. But I changed it to a kind of a graph like this, which at the left we can see the cross-ventilated flats, and on the right-hand side the single-sided ones. Because my focus was on cross-ventilation, so you can see that the vertical and the L-shaped or corner ventilation are more common in my cases. The first model that I tried to analyze and optimize was this one. I can see the plan view of the perspective. So I just changed the window size, just 36 centimeters wide, and then I applied some two different shading devices, overhangs and loops, with again two different window sizes. So all in all, 6 scenarios or 6 cases. Here you can see my first model in detail, and I put my geometry in a dense urban area to represent that, and I did my simulations in 8 wind direction, including that climate data that I already talked about it, and I did my simulations with Autodesk CFD at the first time. Here are my raw data. As you can see, it's really difficult to read and understand. And in terms of number, there are plenty of those. So it was difficult to have any kind of architectural understanding. So I came with this kind of idea, which includes my 6 different wind directions and 8 wind directions and 6 cases that I already talked about. With a very fast look, you can find out that on the right-hand side, with the larger windows, we have a lower temperature. And also in terms of airflow rate, also we have a better airflow, except for 90 and 270 degrees, which the windows are not toward wind, obviously. because I have the data and information for all the rooms and all floors, I can have all these tables in different areas. For example, here you can see that for the first floor living room, for example, because the living room is located in the south, the south facade is exposed to sun and get heated, and this heated air is coming in when the wind direction is from south. So however, we have a better airflow, but we all know that it's not a good or in a good temperature, and we have to avoid it. For the second geometry, as I already discussed, I picked L-shaped or corner ventilated flat, which the geometry looks like this, exactly the same scenario, 6 geometries with different shading scenarios. You can see again in detail. And also almost the same thing happened in the results with larger windows. We already have a 2-3 degrees lower temperature, and also with shading, I mean, with overhangs also we are experiencing a better condition in most cases. And always the same scenario is happening. For the validation, I picked to run again the simulations with butterfly open foam engine in 4 directions because of the time. And here is the comparison between 2 engines, and you can see that the difference range between 2 simulations are normally below 10-15%, except that 90 and 270 degrees that I already talked about, that the airflow is very low and a very small change changes a lot. As a final steps, I try to convert all the information and data about temperature and airflow to PMV and UTCI thermal comfort index for indoor and outdoor. So as we have all this information for specific location and a specific geometry, instead of having this information from EPW files or climate stations, which are normally outside the city or far from the location of the case that we are studying. So we will have a more accurate thermal comfort study. Here is an example that's without considering wind, we will have such these results, and considering with wind with EPW or file or wind speed from climate station, and then with CFD, which is a more accurate way to have the thermal comfort. The second step of my PhD, or the last one, is about developing this workflow as a kind of semi-automated workflow to have your geometry, and you can analyze exactly the same scenario and workflow that I already explained as a parametric way. So you can change the window size, you can change the direction, wind directions, and everything, and run your simulations and optimize it again and again. It's worth mentioning that as a kind of variable, controlling variable in parallel of my study, I was looking at the thermal comfort during winter, and also energy use during winter, because you know that changing window to wall ratio may cause some effects on that also. Thank you so much, and I'm looking for questions at the end.
Thank you so much, Mohammed, for your presentation. It was wonderful and extremely insightful. We do have 2 questions for you. The first one is from Alan. He's asking, for the temperature results, did those include solar heat gain through the windows as well?
Yes. It also includes the solar radiation from the sun also, and the radiation inside the buildings, again from the sun or from the window is coming. Yeah.
Okay. The second question is from Junaid. He wants to know, How closely do the simulation results match the actual conditions on site once a project is built and operational?
Uh, it's a difficult questions because I don't have any information or data about that. But uh, CFD simulations are normally reliable, and but yeah, always they need validation and the case tests. But yeah, I can say it's pretty much reliable or close to the real scale data.
Awesome. Thank you so much.
Thank you.
So, our second presenter is Divyanshu Sood. He is energy systems researcher at University College Dublin, specializing in sustainable building design, data-driven optimization, and indoor environmental quality. His PhD work developed machine learning-based occupancy models and multi-objective optimization frameworks to improve energy use, comfort, air quality in residential buildings. His work bridges research, policy, and practice to advance healthy, energy efficient, and climate responsive housing. Please go ahead, Divyanshu.
Can you see my screen? Okay. Thanks, Abuba, for the introduction. And hi, everyone. So my name is Divyanshu, and today I will be talking. so- And today I will present my work on the life project, which was a part of my PhD, which focuses on assessing the indoor environmental quality and energy efficiency in a range of naturally ventilated residential buildings. And I took the multidisciplinary approach for this. So now to start with, so the motivation for this comes from a well-known strong relationship between the energy consumption and the indoor environmental quality or IEQ. But however, in majority of the studies which focus on the residential dwellings, the energy consumption and IEQ are usually evaluated separately. So that was the motivation to see like how if we consider energy consumption and IEQ at the same time, how does that affect the occupant comfort and health and in the naturally ventilated residential buildings during the design phase as well as the operational phase. So to address this problem, I carried out a longitudinal monitoring campaign of energy consumption and IEQ in the naturally ventilated residential dwelling. So the core aim of the project is to evaluate whether natural ventilation can be used to reduce the energy consumption and prevent overheating in the energy efficient dwellings. So specifically this project Alive, it investigates what are the different ventilation strategies should be there so that building design which considers the building design, occupant behavior, and how does the integration of both affect the energy use and the indoor environmental quality. So this intention of this project is to inform the retrofit and the design strategies that balances the efficiency and the healthy indoor conditions. So now for this, an integrated approach was used. So that approach integrates the site measurements, occupant surveys, energy modeling, simulations, and optimization. So to start with, first I selected the number of houses across Ireland which are energy efficient and are employed with natural ventilation. And the data was collected for a one whole year for the summertime and the winter time. And the data focuses on the energy consumption, CO2 concentration, indoor temperatures, humidity, PM 2.5, and nitrogen dioxide. So I have collected the data for the one year. Once the data was collected, then I did the modeling, and the data which I was collected were used to calibrate the model so that I can accurately estimate the energy consumption and the indoor environmental quality in the residential homes. Just a quick note on here: when I say IEQ, the IEQ in the study focuses on indoor temperature, seconds, and the CO2 concentration. So finally, these integrated models are used to assess the impact of ventilation and occupancy on both energy consumption and IEQ. Now, so to collect the data set, I use two different types of IEQ sensors and one energy sensors. So on the left image, which is a low cost sensors, these are deployed in the houses for over a for over a year, so that they can keep collecting the data, and they collect the data at 1 minute interval, and all the data was saved on the cloud so that can be accessed at any time. The image in the middle, which is high grade IQ sensors, these were installed for 2 weeks in the home, so that we can 2 weeks in the summertime and 2 weeks in the winter time, so that we can calibrate the low cost sensors. Then the last image are the energy sensors, which we deploy over the smart meters, because we did not want to bother the occupants again and again for the data. So these smart energy sensors, they record the data on the smart meter and upload it on the cloud without any intervention. Once I have the data, so I started the modeling. So the modeling was done between the two softwares, Energy Plus and Contem. So this is a co-simulation between these two softwares. Energy Plus provided me the indoor temperatures and the energy consumption, and Contem provided me the time varying airflow and the pressure values, that again was in such then again was included in the Energy Plus model, so that we have better estimation of energy consumption, indoor temperatures, and the CO2 concentration. once the data set once I have the models, so then I started the meta developing the meta model and the multi-objective optimization framework. So in this presentation, I'll show an example of one type of dwelling which I selected for the Ireland. So first, to develop the meta model, I needed the parametric data. So for that, I used the most common housing type in Ireland, which is a semi-detached house. It has 3 floors, and it has 2 floors and one attic, and it is not connected to any other house. A- And then once I have this model, I focus on the natural ventilation. So I use the airflow network in Energy Plus to model the natural ventilation and the infiltration. Then occupancy schedules were also used instead of using the ASHRAE or the SIPSI default schedules. So these are the schedules which I created based on the surveys and the time use survey data. Once all of these are incorporated into the models, I ran the simulations, and and for the base case, I used the sensor data which I collected and validated my base case. And as you can see, the difference in the heating consumption, CO2 concentration greater than 1000 ppm in hours, and the indoor air temperature. So there's approximately 5 to 7% variation between the measured values and the calculated values. Once the base case was validated, I used the JE Plus and the Python to do the parametric simulation, so that I can generate a larger data set. For that, I vary the different geometrical and the non-geometrical parameters, and the U and occupant related parameters as well, to generate a big data set which has all the input parameters shown in the table, and the output parameters are heating energy consumption, thermal discomfort in hours, and the CO2 concentration greater than 1000 ppm in hours. Once I have the data set with me, I use that data set to develop the surrogate model. For that, I use 3 different learning algorithms: gradient boosting, random forest, and support vector machines. And based on the root mean square value and um, mean absolute error, the XGBoost with the gradient boosting performs the best. Once I have the best performing surrogate model, I use that model for the multi-objective optimization using NSGA2. So in this, the fitness function is calculated based on the surrogate model. Once the model is trained and the optimization is complete, it can generate the different Pareto optimal set that balances the thermal discomfort, heating consumption, and the CO2 concentration. So my objective function was to minimize thermal discomfort hours, minimize heating consumption, and minimize the CO2 concentration greater than 1000 ppm in hours. So this table gives an holistic overview of what are the things, different different parameters that can be changed to balance, to make a trade-off between the 3 outputs. So once the meta model based optimization was done, so I compared the results of the meta model based optimization with the physics based optimization. As you can see, I achieved an approximately 80% reduction in the optimization time with a correlation of 0.98 when compared the meta model based optimization with physics based optimization. So it can help us to run various simulations very quickly. Now moving on to the conclusion and the impact. So in this study, I developed a customized framework based on the meta model approach that predicts and optimize energy consumption, thermal comfort, and CO2 concentration. Meta model based approach is fast and reliable with the accuracy of approximately 0.98 compared with the physics based optimization and with a reduction of 80% simulation time. So this project was focused on implement was to we try to inform the policy that integrates energy consumption, IEQ, and the occupant behavior as well. So we have different types of archetypes in Ireland. At the moment, I only focus on the semi-detached, but this in this study, I replicated the methodology for different archetypes as well. And based on the outcomes of the result, we already published a policy paper that recommends what Ireland need to do so that they have better and so that they have better IEQ in the energy efficient homes. So thank you for your attention, and I'm really happy to take any questions.
All right, awesome. Thank you so
Thank you.
much, Divyanshu. We have two questions for you.
Yeah.
First one is, how did you select the households for this project? Is there a database indicating certain households that are energy efficient and uses natural ventilation? And how are the households determined as energy efficient?
So like in Ireland, we have energy performance certificates that signify like what is the energy rating of the house. So if the energy rating was less than 75 kilowatt hour per meter square per year, then it is considered as an A-rated homes. And all the A-rated homes that are built in Ireland are naturally ventilated. So it was easier to select the homes, but it was difficult to convince the occupants to allow them to use their home as a study. And what
Perfect.
was the second part? Sorry.
The second part, I think you answered it. They wanted to know how are the household determined as energy efficient?
Okay. So yeah, these are based
Oh,
on the energy performance certificates.
mhm.
Yeah.
All right. The next question is, for the calibration, do you use total annual value or any granular value? Also, have you collected any occupancy information from the space itself?
Okay, so for the first part for the calibration, so all the IEQ sensors they gave us data at 1 minute interval, and the energy sensors provided us the data at 15 minutes interval. So we used those same intervals to calibrate our models. And for the occupancy, we asked the occupants to fill the activity diary 2 weeks in 2 weeks in every month. So we have the survey data based on like what activities they are doing yeah, at hourly intervals.
All right. How many how much parameters vary between the type of houses?
So in for the type of houses, like as I showed in the last presentation, one is the geometrical parameters and the outer structure of the houses varies. Then all the parameter like U values of the different building elements, solar heat gain coefficients, all the building related parameters, I vary all of those to generate a large data set.
Okay. And did you talk about what mechanical systems the houses have?
So they only have like for the heating they use heat pumps and they are naturally ventilated. So there is no mechanical ventilation in the houses.
All right. Uh, wow, the questions are pouring in for your presentation. People seem very curious. Insects are common around our dwelling areas. Did you consider screens for any of your window for cross ventilation?
And no, I did not consider those.
All right. Was the location of the IAQ sensors varied across the study, or was it fixed at the breathing height?
So those were fixed. Those were fixed. So we installed the sensors at approximately 1.5 meter height in kitchen. living room, and the main bedroom. And those stayed fixed for the year. We did not change the heights.
Okay. And what, I think this is the final question. What was the number of occupants? One of the slides shows CO2 levels of more than 1000 ppm.
So like on all the houses, the number of occupants are 4. So like 2 adults and 2 children.
All right. We will keep an eye out for more questions as they come in.
Okay.
But yes, we
Thank
have
you, ma'am.
our,
Yeah.
thank you so much, Divyanshu. We have our final presenter for today, who is Mohammad Umar. Umar is an architect turned building energy professional, currently working as assistant manager at GBCI India. He specializes in whole building performance analysis, HVAC optimization, and data-driven simulation with research spanning AI applications, air filtration media, and green building decarbonization. His work bridges design, simulation, and policy to advance resilient, low energy, and healthy buildings. Go ahead, Umar.
Thank you so much, Apurva. I'll be sharing my screen now. Hello, everyone. My name is Mohammad Umar, and I'll be presenting my exercise titled Whole Building Design and Cost Benefit Analysis of an Existing Academic Building in India. With increasing existing building stock, much of which is not made as per energy codes, deep energy retrofit, and decarbonization measures are very much important to address the gap. Thus, this is an exercise of a comprehensive whole building design of an existing building. A little bit about me. I'm an architect and a sustainability engineer from New Delhi. I'm a recipient of the Student Modeling Competition Award at the IBPSA-BS 2023, and I'm a gold medalist graduate from the MTech Building Energy Performance Program at SEPT University. Here is my LinkedIn and email in case anyone wants to reach out to me after this presentation. Coming on to my study, the study was conducted as per the whole building performance method of the Energy Conservation Building Code, ECBC 2017. Optimization decisions were not taken solely on the basis of energy, but they were also taken based on energy and cost feasibility. Cost is something that fortunately or unfortunately dominates the conversations. Optimization decisions were also taken with a strong focus on occupant thermal comfort. So this was an existing educational building which was located in Kolkata, West Bengal, which is a warm and humid climate zone, and it's cooling dominated zone with a built up area of 3,200 meters square. It was an exposed brick and RCC building, as you can see in the representational image as well. I used multiple tools such as Design Builder, Energy Plus for the energy simulations, Light Stanza for daylight simulations, Thermal Comfort Assessment Tool by CBE, and MNRE solar rooftop calculations as well. The methodology entailed that architectural modeling of the existing building was done to inform the energy modeling of the standard case. The standard case was then taken through climate analysis, passive strategy identification, and a number of optimizations to finally formulate the proposed case. The strategies for proposed case formulation were existing building study, thermal comfort climate analysis, mixed mode ventilation feasibility, optimization of daylight, building envelope and HVAC, integration of on-site renewable energy, elevated airspeed for thermal comfort, and cost feasibility. Coming to the standard case or the base case, energy model optimization was done so that the simulation time is cut down and it exhibited same thermal behavior, but the model was made much lighter and simulation times were optimized. Thermal zoning tells us that there are not really east or west zones in the building. There are south, north, and core zones mostly. The load profile analysis on the right-hand side shows that there was a 60-40 share of sensible to latent loads. Of course, because this is a warm, humid climate zone, so 40% was dominated by latent loads. Coming to the zone-wise sensible cooling loads, north zone shows an overall higher cooling load than south zone, followed by the core zone. This is little bit of atypical behavior because typically in the northern hemisphere we see south zone showing the highest cooling loads. But given this building was shaded extremely towards the southern side, and the north zone had a much higher sky view factor and window wall ratio than the south, the radiative gains increased much higher. Looking at the extreme right-hand side on the component contribution to the cooling load, radiative gains were something that dominated this contribution by 36%, followed by the conductive gains. And this conductive gains, when broken down at an envelope level, showed that the roof element is the highest, followed by the walls, followed by the glazing. The standard case energy performance index, or the EPI, which is similar to energy use intensity, was 78.4 kilowatt hour per meter square per year. Coming to the daylight optimization strategies were applied, such as increasing the vegetation spacing, especially on the southern side, making the opaque partitions as translucent, and lowering the height of partitions so that more daylight spread is there in the indoor environment, adding light shelves, increasing the VLT glass, adding light shelves, and increasing the surface reflectance of the ceiling surface for better light scattering. When all of these optimization strategies were applied, the base case became daylight compliant on the right, from showing UDI on the ground floor from 23% to 41%. UDI is useful daylight illuminance, which is a similar metric to spatial daylight autonomy. And Energy Conservation Building Code demands that UDI should be minimum 40% of the area for each floor. Mapping the effect on energy use, daylight optimization fortunately showed hardly any energy increment, just a 1% increment in the EPI, and the daylight compliant case showed a 79.1 EPI. Following this, thermal comfort and climate analysis was done. The thermal comfort model taken was the Indian model of adaptive comfort mixed mode. That, combined with the relative humidity, was taken for the natural ventilation feasibility analysis. Night purge ventilation feasibility was also analyzed, but as you can see here on the bottom left, that when RH and DBT both are taken into consideration, the number of feasible days were right down to 4. So night purging or evaporative cooling type of strategies were not feasible. But when looking at the natural ventilation on the top right, it was revealed that 26% of operational hours are actually feasible for mixed mode operation, and 20% of hours were completely feasible, completely comfortable, but you can still use elevated airspeed or ceiling fans to increase the number of MET hours even during that time. Now coming on to the mixed mode ventilation and elevated airspeed. So here the correlation between the window and HVAC operation shows that although there are maximum number of times HVAC operation is required to give MET hours, there is also window operation in certain times in February, March, October, and November, where you can operate windows to get MET hours. There are also durations in December to January, where you don't even need window operation. The indoor environment with the internal heat gains becomes comfortable as it is. The unmet hours required as per ASHRAE 90.1 should be below 300 for each zone. So as you can see in the table here, some zones were exceeding the unmet hours required. Operating the building in mixed mode lowered the EPI by 7%. So this shows the significance of operating building in mixed mode. Now catering to the unmet hours, which are exceeding the 300 limit, introducing cooling effect of elevated airspeed. So I used here the CBE thermal comfort tool that assess thermal comfort as per ASHRAE 55. So what you can see here is, given that the conditions are met, it increases the upper range of the adaptive comfort band by 2 to 3 degrees Celsius, which is a lot. So using ceiling fans for elevated airspeed greatly increases the thermal comfort, and it greatly reduces the unmet hours. Coming to the envelope optimization, the sensitivity analysis was done for each parameter separately, and it was revealed that the high SRI of the roof decreased the EPI by 2.5% with just a 1% cost increment. Only the roof SRI iteration was carried forward and other iterations were ignored because, as a thumb rule, anything that exceeded 10% increment cost was ignored. So not only am I looking at the EUI or the EPI, I'm also looking at the percent increment in cost. So the envelope optimized EPI came down to be 77.1. Coming on to the HVAC system optimization, the first part is selecting the right HVAC system, then optimizing it further. So in the standard case HVAC system, the system tonnage was 58 tons, and it had 23 zones that were being catered to by VRF system and 21 that were catered to by PTAC units. So in the end, when energy use and cost is looked at, the base case itself was the most feasible because it showed the most feasible energy use with the equipment cost. You can see here that even hybrid system was tested. It showed 1% lower energy use, but nearly at 2x cost. Thus, the base case was taken forward. So optimizing the base case forward, optimization strategies that were used were replacing all the PTAC units by VRF. So all the 21 zones were also now catered by VRF. Optimizing the zoning and the right sizing the equipment, changing the fan type, and of course, introducing humidity control because it's a warm, humid climate zone. So that was very important. That reduced overall the EPI by 11%, the highest reduction of any of the strategies by far. The standard case had 58 tonnage of auto-sized equipment. Optimized case had a 49 tonnage. So the final EPI of HVAC optimized system was 66.2 kilowatt hour per meter square per year. Now coming to the conclusion where I wrap up all of these iterations, and this is really the star graph of this assignment, where the EPI of each iteration is summed up along with the project cost on the red line. And the blue dotted line also shows the payback period of each of these iterations. And these iterations are being incrementally added from the left to the right. So this was my starting point, the standard case, which was quite a strict baseline. So what I started was with the standard case itself to be ECBC compliant. That is quite a strict baseline to begin with. Then optimizing daylight for enhancing visual comfort and achieving code compliance. Here onwards, all of the iterations are optimization strategies till the daylight optimization code compliance was achieved. Now, optimizing the envelope lowered EPI by 2.5% at 1% added cost. Mixed mode operation lowered EPI by 7% at 1% added cost. Then elevated airspeed or adding ceiling fans, although it obviously added to the energy use of fans and overall EPI was increased. But this was a necessary measure because it greatly enhanced the thermal comfort. Then these are all the HVAC optimization steps that I talked about earlier. So you can see from the daylight proposed case of 79.1 EPI, which is roughly 25 kBTU per square foot EUI. The optimization strategies were able to bring it down to 66.2 EPI, which is roughly 21 kBTU per square foot per year EUI, which is a 16% reduction. And finally, integrating a 108 kilowatt rooftop solar PV array, it resulted in a net 1/3 energy use of the 66 that was on the left. So this 108 sizing was based on the rooftop area available and all the calculations that were done in a rooftop solar array calculator tool. Wrapping it further, there is this investment packages for stakeholders. This is a very intuitive, very simple graph where any stakeholder, whether it be energy consultant, whether it be an architect, whether it be an economist, they can select how much additional investment they want to do, or they can select what is the payback period they want. So The horizontal dotted line here represents on the y-axis what is the additional savings here, and this inclined line represents what is the cumulative energy cost savings. And wherever these two intersect is the simple payback period. So higher slope of line indicated the shorter payback period. You can see here clearly that if you use all of the cases with the photovoltaic system that was shown in the previous graph, you will have close to a 60 lakh INR additional capex, and you will have a payback period of roughly 4 years. If you do not apply the photovoltaic system, which is quite costly, the additional capex goes down, but the payback period also comes to 6 years or 5 years. And if you just take one or two optimization iterations, the payback period is less and the additional capex is also less, but the savings is very minimal. The payback line is almost parallel to the additional capex. So with this, I end my study. This is my code compliance checklist, and these are my references. Thank you so much.
Thank you so much, Umar. That was a great presentation. We have a bunch of questions for you as well. First question is, what program are you using for assessing the cost of envelope upgrade and HVAC upgrade?
Okay, so as this was an existing building, I had detailed BOQ received from the architect and the builders. And based on that, whatever additional parameter change I applied, I researched the real market rate. And that's how I was able to get the cost increment.
Okay. The
Yep.
next question is, the load profile chart seems pretty interesting. The unit is kilowatt. Are those numbers the peak load of that month?
No, those are the cumulative of the entire year. That's why they are in thousands of kilowatt.
Okay. The next one is, were the energy model results calibrated with actual operational building?
Yes. So this was done in a kind of inverted fashion where uh, most of the parameters were measured on site and then they were programmed into the energy model. The only things or only parameters changed were as per the energy conservation building code compliance. Other things were kept as is.
Okay. And how exactly did humidity control reduce the EPI? And what humidity control system or device was proposed?
So there was no humidity control device as such. At the cooling coil itself, I programmed the settings uh, to change the set point from 12 degree to 10 degrees Celsius. So not only was it controlling the humidity at source, it was also consuming less energy.
All right. How are you calculating the cost for each iterations?
So for the cost of each iteration, I'm just changing one parameter, either may it be envelope, may it be additional HVAC systems that I'm introducing. So per parameter, I researched what is the actual market cost, and that's how I added it to the base cost of the standard case.
Awesome. I think one final question for you is, was any solar simulation done to accurately judge the annual energy generation from the PV?
No, solar generation was not in scope of the energy simulation, but it was done from a credible tool of Ministry of Renewable Energy India, and that annual solar rooftop calculator tool gave the precise size and the precise generation based on the location and the latitude values.
All right. Awesome. Thank you so much, Umar.
Yeah.
We have one more question.
Yeah.
So about the peak load question, there's a follow-up that if they were cumulative, shouldn't the unit be kilowatt hours that you are adding a kilowatt load over a period of time?
Yeah. It should be, I think. Yeah.
All right, maybe just a typo on your end. No
Yeah.
worries. We do have a question for Mohammad. We have two questions actually. One is, how did you incorporate CFD in Grasshopper?
Yeah, I use normally Butterfly or Edit3D plugins, which both of them work with OpenFOAM engine.
All right. And why would you conduct natural ventilation studies in summer months but thermal comfort in winter?
Yeah, good question. Because if you remember, one of my scenarios was opening the windows or enlarging the windows actually. So it increased the window to bar ratio, and it might affect because my research is in Poland and it's a cold climate, so it might affect on the insulation and thermal comfort and heating load of the homes during winter. So I'm just checking that variable because I don't want to affect the thermal comfort during the winter.
All right, thank you. Let me see if we have more questions. I don't see any open questions right now. Please keep sending your questions. I'm sure our presenters love listening to your questions and answering them. And meanwhile, let me get back to a little bit of my agenda here. So while we wait, we do have 8 minutes left in our webinar. And while we wait for more questions to come in, I wanted to say a big thank you to our presenters. We hope you enjoyed sharing your project, and we are so glad that IBPSA USA could give you this platform to showcase your work. And our audience, thank you so much. You've been fantastic asking questions and supporting our students and emerging professionals along the way. It really makes a huge difference. And we have more events coming up. We have career pathway mapping. We have effects of occupant thermostat webinar. And we have our semi-annual meeting coming up early next year. And of course, we have our fantastic SimBuild coming early next year as well. So keep an eye out on our IBPSA USA website for what's next. Also, don't forget to subscribe to our YouTube channel to catch today's recording, and we have a bunch of other webinars as well. One final call for questions. Do we have any? Well, we don't. I guess our people already asked you a bunch of questions. So thank you
If
so much,
we don't
everyone.
have a question, can I
Yeah.
circle back to that question about the cooling load?
Yeah, sure. Go
So
ahead.
the cooling or heating load is always measured in kilowatt, and the energy is what energy consumption or savings are what is calculated in kilowatt hour. The only reason I added overall cooling loads and not showed any peak cooling load was to subjectively and precisely judge what is the distribution of the sensible and the latent load. That's why I added it throughout the entire year. Thank you.
All right. Thank you for the clarification. I don't see any other response to that. Any more questions? Anything else? Going once, going twice. All right. Thank you so much, everyone. Hope you have a wonderful rest of your day and see you soon next time. Thank you.
Thank you.
Thank you.
Thank you.
Goodbye.
Thanks, Apurva.